Albert Einstein's Special Theory of Relativity in Approximately 5 Minutes by Graham Arthur Mackenzie of Explaining Concepts. Believe it or not, Albert Einstein's Special Theory of Relativity is so simple it can be described in 2 sentences. Number 1, the laws of physics should work equally well for everyone, no matter how fast they're moving. And number 2, the most accurate method for translating measurements of distances and times between 2 or more observers moving at different constant speeds is the Lorentz transformation. Of course, something that is simple to describe is not necessarily easy to understand, so I'm going to try my best to explain it to you. Of all the ideas contained in the 2-sentence description given above, I'm going to assume that the one that will give the most people the most trouble is the one about the Lorentz transformation. What exactly is the Lorentz transformation? Well, it is a transformation named after the man who invented it, Hendrik Lorentz. Okay, then what is a transformation? Well, it is basically what the second sentence says it is, a method for translating measurements of distances and times between 2 or more observers moving at different constant speeds. I'll explain more about why we need transformations in a minute. Considering that the bit about the Lorentz transformation is fully half of the whole package here, understanding it as well as possible is obviously going to be crucial to understanding the special theory of relativity. How we get from the Lorentz transformation to E equals mc squared is going to be laid out in the course of this presentation. Explaining mathematical concepts in non-mathematical language always presents a particular kind of challenge, but if you are up to trying to understand it, I am up to trying to explain it. For hundreds of years before Lorentz came up with his transformation, physicists used one invented by the great Italian physicist Galileo Galilei called, naturally, the Galilean transformation. Galileo was the first scientist to state definitively that the laws of physics should work equally well for everyone no matter how fast they are moving, as I put it in the previous paragraph, and he called this belief of his the principle of relativity. Galileo declared this principle to be one of the defining features of a physical law, and he embodied it in the equations of his transformation. Or, to put it another way, Galileo came up with his transformation to formalize his belief that a physical law was something that should work equally well for everyone, regardless of the speed at which they are moving. All this means is that if I were standing still, and you were traveling at 100 kilometers per hour, for example, and we both measured the distances and times relating to any particular physical phenomenon, our measurements would differ based on the speeds at which we are moving, but the relationships between these various measurements, in other words, the law that describes such relationships, would remain the same. And a transformation is the means by which we could translate my measurements to fit your state of motion, or vice versa, such that the consistency of such relationships would be preserved. Galileo's principle of relativity has never been refuted experimentally in all of the hundreds of years of its widespread use, which is why Einstein felt confident including it as the basis of his special theory of relativity. Einstein included the essence of Galileo's transformation, the principle of relativity, as the basis of his special theory of relativity, but explicitly stated that, for the purposes of transformation, the most accurate one available is Lorentz's. What exactly did the Lorentz transformation have going for it that the Galilean one did not? The answer is that the Lorentz transformation, unlike the Galilean, accounted in its equations for one of the most interesting facts about light, namely that light has the same speed for everyone, regardless of their constant speed of motion. This is an unusual phenomenon compared with most people's everyday experience, as well as the central point to grasp in understanding the special theory of relativity, so it bears some explanation. According to the Galilean transformation, an individual at rest will perceive light to be traveling at its natural speed of approximately 300,000 kilometers per second. Therefore, an individual chasing a light particle at 100,000 kilometers per second should naturally perceive it to be traveling at 200,000, but this is not what happens. In actuality, both people perceive light to be moving at 300,000 kilometers per second, regardless of their constant motion. And the Lorentz transformation, unlike the Galilean one, reflects this fact. How this fact came to be recognized in the first place will be explained in the next couple of paragraphs. Ever since the early 1800s, when light was recognized as being a wave phenomenon, physicists had been looking for the stuff that light waves travel through in the same way that ocean waves travel through water and sound waves travel through air. As is common practice in science, physicists were able to say theoretically what kind of properties the stuff should have before they were able to detect its existence experimentally. They said it was obviously undetectable by any of our five senses, pervasive throughout the entire universe, and simultaneously more rigid than any solid and more diffuse than any gas known to humankind, and they named it ether. By the 1880s, things had progressed far enough technologically that two men, Albert Michelson and Edward Morley, were able to perform a series of experiments that they had every reason to believe would be able to provide the long-sought-after definitive proof for the existence of ether. The basic idea was that if the ether was pervasive all throughout the universe, and light was traveling relative to the ether, as the stuff it moved through, then, according to the Galilean transformation, the Earth's motion through the ether should have a noticeable effect on the measured speed of light. As an analogy, suggested by Michelson himself, imagine two swimmers who happen to swim at exactly the same speed, having a race in a swift river. One swimmer swims upstream for 10 meters and then back downstream for 10, while the other swims cross-stream for 10 meters and then back again, with the both of them ending up in the exact place that they began. In such a situation, the swimmer going cross-stream will win every time. For our analogy, the Earth is the riverbank, the river water is the ether, the swift motion of the river is the Earth's swift motion through the ether, and the swimmers are light particles. If the mechanics of the situation are still not clear to you, don't worry about it, because what happened was that every time Michelson and Morley performed their experiment, they always got exactly the same speed for light, as we would have guessed based on what we've learned so far, thereby proving definitively that the ether absolutely did not exist. Like most people, physicists are loath to give up an idea they are fond of in the face of inconvenient facts without a fight, and so it was with Michelson and Morley's experimental refutation of the existence of the ether. Upon receiving news of their results, many physicists went immediately to work trying to explain them away theoretically in an attempt to save the notion of the ether. The most successful of these attempts was made by our friend Hendrik Lorentz, who hypothesized that perhaps the ether was having some as-of-yet not-understood effect on the arms of the measuring instruments that Michelson and Morley were using, causing them to shrink in the direction of the Earth's motion through the ether. In our swimmer metaphor, this would be the same as saying, had they, against our expectations, always arrived back at the starting point at the exact same time, that maybe it was due to the water causing the width of the river to grow proportionately to the time difference we would have expected to see between the two swimmers. This hypothesis was known as the Lorentz contraction, and it would eventually become our all-important Lorentz transformation. It was a clever idea, and its equations accounted perfectly for Michelson and Morley's unexpected experimental results, as they were designed to do. But, unfortunately, the conceptual basis of the idea was wrong. There is no ether, and therefore no actual contraction. And so it had the fatal flaw of leading to other problems that were intellectually much more troubling than the one it was invented to address. Equipped with the correct conceptual understanding, Einstein would come along years later to preserve the effective mathematics of the Lorentz transformation and, as we know, incorporate it into his special theory of relativity as a fundamental element. Einstein recounted, many years after the fact, that so far as he could remember, he had been unaware of the results of Michelson and Morley's experiment when he developed his special theory of relativity in the early 1900s, publishing it in 1905. Indeed, Einstein's approach to the problems dealt with by the special theory followed a purely theoretical path. It was the culmination of a process begun as a teenager by asking himself the question, what would a person traveling at the speed of light see when looking in a mirror held out in front of him or herself? At the time that Einstein asked this question of himself, before he had invented the special theory of relativity, an informed answer would have been, the person would see a mirror without a reflection, because traveling at the speed of light means that the light which should have reflected off of the person's face, traveled to the mirror, and returned to the person's eye as their mirror image, can never actually outpace their face. But this implies a violation of Galileo's principle of relativity that the laws of physics should work equally well for everyone no matter how fast they are moving, because the person moving at the speed of light would know when this is the case. Their reflection would vanish from a mirror held out in the direction of their motion. Einstein's solution to this paradox, as we know, was to hypothesize that the speed of light must be the same for everyone, regardless of their constant speed of motion. This hypothesis would eventually be considered verified by Michelson and Morley's test results, and laws of motion incorporating it would eventually be developed based upon Lorenz's transformation. Logical though Einstein's hypothesis was, it led to a number of scientific consequences that, even to Einstein himself, initially seemed too strange to be true. However, all of the major ones that I am about to outline in the next few paragraphs have been very successfully verified over the years. To begin with, let's flesh out the example I described back in the simplified version of paragraph 3, the one about the person observing the speed of light while both standing still and moving at 100,000 kilometers per second. I hope you will remember that in both cases, the person saw the light running away from them at its natural speed of 300,000 kilometers per second. To make the example a little clearer, imagine that instead of one person we are talking about two, one who is standing still on the side of a road that the other is driving on at 100,000 kilometers per second. Talk about a hot rod. Now, imagine that at the exact moment the person in the car passes the person standing on the side of the road, a flash of light goes off directly over their heads, like on a camera. Roughly speaking, when a source of light flashes, a sphere of light called, what else, a light sphere, expands in all directions from the source, sort of like a balloon getting blown up. In our situation, both the person standing still and the person traveling at 100,000 kilometers per second would consider themselves to be at the center of the light sphere as it expands outwards into space. How is such a thing possible? Only because the two people make mutually differing measurements of space and time. Both individuals will consider the other one to be slowing down and shrinking in the direction of their motion. Physicists used to think that measurements of space and time were the same for everyone, and that the speed of light was relative. But they had it exactly backwards. The speed of light is the same for everyone, and measurements of space and time are relative. This is where the theory of relativity gets its name. Here is another way to look at the point made in the last paragraph. Everybody's measurements of spaces and times depend on their judgment of simultaneity. In the case of times, the reason for this is obvious. To be able to know if two things happen at different times, you have to have an idea of what it means for two things to happen at the same time. With spaces, it's a bit more complex, but to put it simply, you can't measure something's spatial dimensions without knowing that two ends of a ruler are in place at the same time. Therefore, the fact that light has the same speed for all observers is going to have a tremendous impact on these kinds of measurements, since it dictates that people moving at different constant speeds will have different judgments of simultaneity. It follows from this fact that describing an object's position in either only space or only time is no longer going to suffice to locate it accurately. We're going to need to know its location in both space and time. This is why, after Einstein's innovation, physicists could no longer talk accurately about a thing's location in either only the 3 dimensions of space or the 1 dimension of time, but rather had to discuss its location in the 4 dimensions of space-time. One of the things that physicists love about theories is that they answer questions that they were not invented to address. Einstein dictated that the Lorentz transformation is the most accurate way of translating measurements of distances and times between two observers moving at different constant speeds because its equations account for the fact that light has the same speed for all observers. But one of the unexpected things the transformation's equations indicate is that nothing can move faster than the speed of light. If you plug a velocity greater than the speed of light into the Lorentz transformation, it gives you answers that are physically meaningless. Furthermore, adding together as many velocities less than the speed of light as you like under the Lorentz transformation will never add up to one greater than or equal to the speed of light. If you are unfamiliar with the ways of physics, you might be saying to yourself, but that's just something the equations do. That doesn't mean that that's what happens in real life, despite the fact that depending on reliable equations in just such circumstances is a tried and true method of physics. If you are such a person, I will tell you that it has been experimentally verified that increasing a particle's velocity to that of the speed of light would require an infinite amount of energy. In other words, it can't be done. Only light particles, and a handful of similar objects, can move at the speed of light, and they can never move slower than this. At last, we arrive at that shorthand for genius, the so-called most famous equation of all time, E equals mc squared. Now, just like the special theory of relativity itself, the essence of this equation is actually quite simple to explain. However, unlike the theory, it is also easy to understand. Put simply, the equation says that energy and mass are the same thing. I will break it down into English for you. Energy, E, equals mass, m, times, it's implied, the speed of light squared, c squared. Squared means times itself. As I hope you have learned by now, the speed of light is a very large number, 300,000 kilometers per second. And a very large number times itself makes a very, very large number, which means that if an object's energy, E, is equal to its mass, m, times a very, very large number, c squared, then a little bit of mass must equal a very, very large amount of energy, and this is absolutely true. E equals mc squared helps explain such things as how our sun expends enough energy to heat and light our planet and help its plants grow, and how a relatively small nuclear bomb can pack enough power to destroy an entire city. Even stranger, E equals mc squared dictates that it is possible for one person observing an object to see it display only the qualities of mass, while another person sees it display only the qualities of energy, in the same way that the relativity of spaces and times means that one observer can perceive two events to be separated only by space, while another can perceive the events to be separated only by time. Well, here we are at the end. As promised, we made it all the way from an explanation of the heart of the special theory of relativity, the Lorentz transformation, to a description of its most famous outcome, the equation E equals mc squared. I hope that I have succeeded in explaining it to you well enough for you to understand it at least a little bit better now than you did when we began. Of course, the beauty of a presentation such as this is how easy it is to go back to the beginning. But before we sign off, I have to explain one more thing to you. I would be remiss in letting you finish this presentation with the impression that the moral of this story is that for hundreds of years physicists thought they knew exactly how the world worked, that is, by the rules of the Galilean transformation, and then they found out that they had been wrong all along, but they were sure now that they were really right this time, that is, by using the Lorentz transformation. The fact is, science is a much more pragmatic endeavor than this. Yes, physicists can often walk around like a bunch of smarty-pants know-it-alls. I say this as an aspiring physicist. But that is because their theories consistently give them ample reason to have a great degree of confidence that they understand fairly well a number of interesting things about the way the world works. In reality, physicists are always looking for ways to prove themselves, or rather their colleagues, wrong. And the best ones, despite their natural human tendencies towards all kinds of prejudices and biases, maintain a high degree of skepticism and incredulousness towards themselves and their theories. All of this is to say that what physicists learned is not that Galileo was wrong and Lorentz right. After all, the Galilean transformation wouldn't have worked so well for hundreds of years if it were fundamentally wrong, but rather that it is a matter of range of applicability. The Galilean transformation worked, and continues to work, perfectly well in its natural domain of applicability to mostly earthbound phenomenon. But it turns out that the Lorentz transformation works well not just on Earth, but also across the whole universe, where the effects of light's special behavior are much more noticeable. However, at low speeds, where such effects are unimportant, the equations of the Lorentz transformation are reduced to those of the Galilean. This kind of steady improvement of models and information is overwhelmingly common in science. In fact, there is some evidence that the special theory of relativity, and its bigger cousin, the general theory of relativity, may itself be a special case of yet an even more general theory, whose discovery hopefully lies somewhere in our future. My fondest hope is that you are the one who discovers this more general theory, and that this presentation is the thing that got you started on your path. Good luck!